Oh, I see myself, so I think the stream started. Right. Good evening, everybody. I'm going to talk about solutions of Google Code Jam problems from this round 2 of 2021. Link is in the description, and we'll see the problems here too. I got 120th place, which is not that bad. I was just slow. The best time was 36 minutes by Radeusz, with I think no wrong penalties. Then Kevin got 36 minutes as well, but half a minute worse time. Then Maroon from Japan. Gennady is 5th, and I am 120th, just because I had twice worse time. Polygon problem. Yeah, I did pre-processing in that problem. Right, the plan is pretty simple today. We will just go through problems one by one, and I will try to be quite brief. This stream will not be very long. And if you have questions about problems, about stuff that I'm discussing, then of course, ask them in the chat, preferably at me. And if you have unrelated questions, then go to Discord or YouTube comments or something like that. Not to, mess up with the flow of the stream. Okay, I think we're good to start. Minimum sort. In the first one, we were able to ask about minimum in an interval, and we need to sort it. We need to sort the sequence by swapping stuff. The easiest thing we can do is, how is it called? Insertion sort? Not even that. I don't know the name of this sort, but one of quite easy things we can do in sorting is we can find minimum and put it in the first place. Right? Nothing too complicated. If you see a sequence like 6, 4, 2, 3, 10, then you can scan the sequence, find the minimum. Minimum is here. What do we do with that? We swap it with the first position. So with 6 in this case. After the swap, the sequence looks like that. And we need to sort this thing. So the pseudocode is, start from this position, from position I equals 0, and always from I to the end, find the minimum, and put it on position I. After that, look at the next I. Here, find the minimum, put it on this position by a single swap, and so on. But in this problem, what will be the cost of queries? Well, when we ask about the whole sequence, our cost is just the 10 to 8th. Let's say that the cost is just 1, divided by length of the interval we ask about. Then in the next step, this is the cost, and then this is the cost, and so on. And eventually you get this cost of asking about comparison of two last elements. And you should know, if you are on this level of Google Code Jam, that this is around natural logarithm of n. Even if you estimate it as binary logarithm of n, it's then for sure around 6, because n is 100, and we know that binary logarithm of 64 is 6, apparently. Yeah, 6. And we were allowed the cost of 6. But here we don't have this last step. Normally we here say this. So it turns out that this sums up to around 4.8 or 4.1, I don't remember. 4 point something. Selection sort. All right, so this is selection sort. Instead of immediately implementing this, the first thing I implemented, you will see that in the recording from the contest, is I wrote a program to print this sum. I summed up from half through 1/3, 1/4, up to 1 over 100. The printed result was 4 point something, so I knew that this is below 6. We're good. We can implement this. That's it here. Let's move to the second problem. Matrigons. There was something going on about regular convex polygons, And long story short, we are able to use some polygons, but every next one must be divisible by the previous one. If Wolfram Alpha, yeah, you can do that in Wolfram Alpha too. If somebody doesn't know, Wolfram Alpha is very smart online math calculator. You can solve equations. For example, write down 2y plus x equals 6, comma, y minus 5x is equal 10, enter, and we will get a solution. You can also find the sum of values from this to that. Very useful thing, Wolfram Alpha. Now, in this problem, matrigons, I guess I need some drawing. If you want to put one polygon perfectly in the other, this is problem B, then number of vertices must be divisible. For example, if you have hexagon, then you cannot put a perfect square there. No matter how you rotate it. Like, this is rectangle, and this is, I don't know what this will be, some kind of, it's not a square, but you can put a triangle. And generally, if you have, let's say here we have n equal to 50 vertices, then we can't exactly choose every, let's say, 10th vertex, and from this we will get 5gon. There is a name for that, pentagon, something like that, right? Every next n must be divisible. And then what the problem says is we want to draw a few of those. Every next one must be divisible by the previous one. In example, they talked about triangle, then hexagon, and then something with 24 vertices. This sums up to 33. Now, given the sum of values, here 33, that's the first sample test, we need to represent it as the biggest possible, not the biggest, longest possible sum of values divisible by one another. Here the answer is 3 because we got 1, 2, 3 values. And the first problem must be, the first value must be at least 3 because this must be at least triangle. When you upload your contest stream, I guess right about now. Actually, I will do it here. Videos, I'm doing this now. Okay, this will be temporary, I guess. Where are the problems? No, I wasn't prepared because the contest just finished. This will do the job for now. Okay, the video is now published on the main channel. Yep, it is there. I will paste the link in the chat. But you know, you can go to the next channel. Stream is not visible on Codeforces. Okay, thank you for noticing. That's pretty bad because I think all the participants who are interested actually use Codeforces. Well, anyway, let's continue. First number must be at least 3. Every next one must be divisible by the previous number. How many numbers we can use at most to get the given sum? Sum is like 100,000 or 1 million. And there are multiple test cases. If I tell you that the sum must be 33, you can actually very easily say what can be the first number. The first number here for sure cannot be 5. Why? Because if this is 5, then every next number is multiple of 5, so the whole sum is divisible by 5. Another way to write down this sum is to say that this is 3 times 1 plus 2 plus 6. Everything is divisible by 3, and then there are some multipliers. So what can we do when we are given 33? We can check its divisors. For every divisor, consider this to be the smallest number. And actually, let's forget about the numbers here. We don't know that. We just know that there is 3. And then other values are multiples of 3. So still, 3 is before the brackets. And here I need something with sum equal to 10. And the problem becomes just a smaller version of kind of the same problem. We want to here get a sequence of numbers. Actually, the first number should be at least 2. It's allowed to here put 2. It just means that, for example, we get 5 gone and then 10 gone. This is allowed. We can have a multiple of 2. I mean, we can have double the previous number of vertices. So here we have this small subproblem. Represent 10 as the sum of as many numbers as you can, such that every next number is multiple of the previous one, and the first number is at least 2. Where's monogon? That's not allowed in this problem. Yep, so if you use... I used preprocessing here instead of doing something separately for every test case. Pseudocode for preprocessing is something like that. For every n, from let's say 2 up to the maximum allowed, I don't know, 10 to 5, 10 to 6, one of those two. For each of them, for every divisor, x in divisors of n, consider what did we do for 33? We said that 3 is a divisor, so maybe we have 3 multiplied by 1 plus some other stuff. So n divided by x is this, minus 1 we will get what we need remaining, this. So we consider going kind of recursively to smaller subproblem, like that, and roughly we have this. Answer of n is maximize it with answer of this guy plus 1. 1 because I already used one number here, and the only detail here is this answer should be for multiples of 2 and bigger, not 3 and bigger. So this is answer of 2 and bigger, where first number is 2 or bigger, and here this is 3 or bigger. This is pseudocode. How do I get divisors? I run primesif and I collect all of them. In nlog n, I can collect all divisors of all numbers from 1 to 1 million. Thank you, Timothy. That's the pseudocode. Quick look at the actual code. Matrigons. I first run the primesif to find all the divisors. Then for me, array fake is what is the answer if the first number can be 2 or bigger. So I can just run this very simple DP. Fake of n is maximize fake of n with 1 plus fake of n divided by x minus 1. Do that for all the divisors. And then also compute real answers for 3 or bigger. It's the same thing, just we have an if that this first value, the first divisor we use, is at least 3. And that's it. Then in test case, I read n and print answer of n. I wondered if maybe every test case can be solved separately without memoization, but I'm not sure about that. I don't know if we will trigger a lot of values with the same test case. Just to be sure, I used this method. Okay, second problem done. Was the third problem. Hidden pancakes. This one wasn't easy for sure. How many people solved it? 1100 solved big version of hidden pancakes. So I guess it was needed. What's the threshold? What's position number 1000? Yeah, you needed ABC. You needed to solve C big. So I'm guessing that most people are interested in this solution. Microcontrollers? No, I haven't. When seeing this problem, I think you should think about the stack, and I will explain why. This is problem C, pancakes. we put a permutation of numbers from 1 to n in some order in, let's say, a stack. We put something of size 2 at the, or let's say 4 at the bottom, then 2, then this is a valid stack. But then when we put here 3, we kind of erase 2. 2 is hidden. They said that there is a pancake of size 4, on the top of that pancake of size 2, then pancake of size 3. Then when you look from above, you only see this one of size 3 and of size 4. 2 is popped. I would say this is similar to problems like minimum sliding window, where for every interval of size k you need to find the minimum, and you do that in O of n with monotonic queue or monotonic stack. It's very similar. Or how in linear time we can solve max histogram. How is it called? Given histogram, find max rectangle area. Also solvable with a stack, and I think you should think about something similar. Please, guys, use English in the chat. 2 to nth power solution is strange. How does it come from? I don't know. I went straight to polynomial. Congratulations on 120th and advancing. Thank you, Snapdragon, but also I don't treat this as an achievement. I would treat top 5, I guess, as an achievement. All right, here. If we are just given a permutation and we need to simulate this, we use a stack. So maybe if we don't know a permutation, oh, what's the problem? I need to tell you what's the problem. We know that the pancakes come in some order. After every new pancake, you're given information how many pancakes are visible when looking from the top. In this case, first we see 1 pancake from the top. Here we see 2. Here 1 is covered, so instead of 3 we see 2. And then maybe this would cover everything, so we would see 1. Let's say then this kind of pancake and this one, it would be 2 and 3. That's an example. What can happen? If the next number is bigger than the previous one, it can only be bigger by 1, because when we get a new pancake, we see 1 more pancake at most. If the next number is greater than the previous one by 2 or bigger, by 2 or more, then we need to say impossible. We say 0 ways. Other than that, we need to count the number of permutations that satisfy this condition, this sequence of counts of visible pancakes. Achievement is bit tourist, says Eknerwala. I guess so. But then it's more about tourists performing badly, not about you performing well. So I don't know about this achievement. But of course, still, by the way, I'm not saying that being even top 1000 is bad. In the past, I got some good places, so now the bar is high for me, and I'm not that happy about top 120. All right. What do we know? Well, when we simulate this, we use a stack. So what about using stack as well? I can show you my drawing from the contest. It's here. I drew some kind of example, and then I thought about sequence of what pops what, I guess. If we write down a sequence of values, and we know that we have some kind of stack, like the first pancake was of size 8, then there was 6, 7, which erased 6, 5 and 2, and now comes 6. I know that there are some things in active stack. I can store indices of them, and 6 pops some of them, and watch out, 6 stops when looking at the previous greater number. Also, we are not allowed repetitions, but it doesn't matter. Let's say this is 4. Green arrow says what is the previous bigger element, and given the sizes, let's see here, we don't know what is the value of 6. We only know that something was erased. Let's say we know this stack, and here comes some element, and we know that A second ago, 4 elements were visible, and now 3 elements will be visible. Question mark maybe is bad if those are dots too. Pop, pop. So in yellow. Yellow is the current stack. Size of this stack is 4. 4 visible pancakes. Now comes a new element. We don't know that. We don't know what it is. Let's say this is some unknown x. But you know, after you put x there, 3 elements will be visible. So apparently x erased this guy, this one. And for x, this last element in the stack right now is previous bigger element. Now 5 is removed, 2 is removed, those are no longer in the stack, x is in the stack, and so it deserves a yellow dot. And we can continue. If we knew what are the positions of values still not erased, still visible, then if somebody tells us now how many will be visible, we know then how many are popped. The formula for that is, I think, 4 plus 1 minus 3. It's always how many were visible. Now plus 1 because we put a new guy, so we expect that many to be visible. But we got that many visible. Instead of 5, we got 3, so 2 were popped. This is formula for how many were popped. The previous value plus 1 minus new value. We pop them with pop back from the stack, and or with pop, and then we put this blue arrow. It turns out that the arrows are enough for us to solve the problem. And this is my analysis from the contest. Let's see what I did. Some arrows can go to the left of the sequence. This guy doesn't have anything bigger than it on the left, so I will put an arrow to a fake vertex here. Maybe this one also, the previous greater is here. Maybe for this one, this is previous greater. Maybe for this one, this is previous greater, and so on. You can easily prove that this is impossible situation. I leave it to you as homework exercise. This is impossible. You cannot get that. Try to construct this and you will see from inequalities. Okay, so that's not possible. And already this seems promising because we have some kind of structure when some intervals are within other intervals. You know, a little bit like this, where if you draw interval for every green thing, oh, sorry, I need to answer the phone. Sadly, I need a 5 to 10 minute break. After the break, I will finish discussing this problem and the last one. Sorry about this. Here we have, as always, a professional timer. We're now in the middle of discussing C. Right, see you. Hello, hello. Sorry for double the time. Horrible sound. Did you see it? Did you hear it? Oh. I need some water, then we start. Right. We were talking about problem C, and what? We said that using the data from the input, we can, for every position, find previous greater element. And the last thing I said is that it's promising because they have some interval within interval kind of structure. This hopefully will give us the P solution on intervals or something like that. Just like brackets, you know, if you need to say what's the value of 5 plus 7 times 1 plus 2 plus 3 and this divided by 2. How do we compute this? The main bracket, the main expression is this divided by that, or let's say 2 is more complicated, it's 2 plus 2. We compute this, we compute that, and then we combine, in this case using division. How do we compute this? Well, by combining two parts. These have a similar structure, a bit more complicated. As I said, the arrows, those arrows, they cannot cross. Maybe I can as well say why they cannot cross. Because what? Let's say that for this element, this one is previous greater. Like maybe this is 5 and this is 8. And everything here is then smaller than 5. Then what can this mean? For this guy, everything here is smaller, so I'm 6 or greater. This is 6 plus. And for me, this is greater element, so this is 7 plus. But then for 5, 7 is even bigger than 5. So this arrow cannot happen. It would be like that instead. So this is impossible. Now, the actual solution. The actual solution to C. We simulate the stack, and as I told you, in a stack we keep indices of currently visible pancakes. Then when we get new number in the input, thanks to this we know how many pancakes should be popped, and new one appears, and we have this green arrow to previous greater element. In particular, the very first number, let's say it's fake infinity. So everything that doesn't have, if this is 8, and those numbers are smaller than 8, then the arrow is like that, to position -1. If those are smaller than 8. Okay, then let's say that there are some elements who point to this fake element. Maybe those 3. The other elements actually how they are some independent parts. So maybe we will solve them independently and combine. But even better, if I know that those are arrows pointing to the fake infinity at the beginning, and all the other arrows are pointing to something else, I know that this is maximum in the whole sequence. For this element, let's say that this is 8. For him, previous greater is infinity, so everything here is smaller than 8. And if there was here something bigger than 8, like 9, then it wouldn't stop, like the next number greater than 8, it would point all the way over there. So, the rightmost green arrow pointing towards fake infinity at the beginning, this must be the biggest element in the sequence, so just element n. And from here, all the arrows will point here inside or maybe to this 8. And of course, this part is independent because arrows only go to the left. So we have 2 independent parts, this one and this one. We can solve them separately. And when we look at it, let's say we look at this part, it's okay to still say that just to the left of me there is fake infinity, because this 8 is greater than anything here. So when we go recursively to solve this right yellow part, we can say that this is infinity. Doesn't matter. The rightmost green arrow pointing to infinity is also the rightmost one in the input. Oh! Interesting. Yeah, you're right, of course. If something is 1, how can we find maximum in the whole sequence, the biggest pancake? If pancake is greater than anything before, then it's the only one visible from the top. Okay, the last one in the input is the biggest pancake. Good observation. Thank you, Snapdragon. Prebig, stop. Oh, never mind. I wanted to tell you not to repeat comments, but actually you now at me, so that's fine. At least it's different. Yeah, I will show you my solution, so you will see if I used it or not. I don't know if I don't show you a solution with this multinomial coefficient, then it means it's not needed, right? Okay, what now? We need to find this rightmost green arrow pointing towards this index -1, then go recursively to 2 yellow parts and solve them. What do I do here inside? I need to find the rightmost green arrow that starts somewhere here and ends there. Or in general, how do I solve interval of indices from L to R? I look at index L-1 and I say that there is some infinity there. And among arrows from interval LR to this infinity, I find the rightmost one. In this case, it's here. I say this must be maximum. Let's recursively go to 2 smaller parts. And let's say how many ways there are to solve them. And then we need to combine. That's very common in combinatorics. If those 2 parts are independent, let's say the left one is of size 4, the right one is of size 2. Then, very standard combinatorics trick, among all 6 elements, we need to choose 4 of them to say they go to the left part. And the remaining 2 of them will go to the right part. And then when we go recursively to left and right part, we kind of already tell them, okay, we chose some elements that you will need to use, you just tell us how many ways there are to reorder that. So, answer of LR is answer of Lx minus 1 times answer of x plus 1 comma r, where x is this rightmost green arrow pointing towards L minus 1, times this 6 choose 4 binomial coefficient, where this is, of course, it comes from size of this yellow part and this yellow part. So formally it will be what? Choose of, I think, r minus l, comma, let's say l minus x minus l plus minus 1. How many elements there are in total in those 2 yellow areas, comma, out of them we choose those elements that will go to the left interval. How many times I won CodeGem? In past 5 years, the answer to this question is very easy for everybody in the world except one person. Okay, how do we find the rightmost green arrow pointing towards some index? For what I did is, for every index I had something like that. This is vector of indices going towards, like pointing to position I. So when I look at position I, for any I know what green arrows come here. I know their indices, they are sorted, and I can then binary search. When I deal with interval LR, then I look at position L-1, I have a sorted vector of green arrows coming here, and I will binary search to find the biggest value not exceeding R, or rightmost green arrow not exceeding R. It's something like, let's say, upper bound for R. I don't want this strange autocorrect. No, thank you. -1 in terms of iterators. Something like that. Easy binary search. How do we find this? We need to pre-compute factorials, inverse of factorials, modulo billion 7, and then there's easy formula for that. Done. You needed this apparently today to get to the next round of CodeGem, but if you solved similar problems, and they are quite often in competitive programming contests, then yeah, this should be easy. That's C. Tell me if you have any questions, and then we move to D. Okay. Instead of using choose, you can take probabilistic view, and then answer is n factorial divided by product. Yeah, instead of counting, almost always we can say what's the probability that, no, I will shortly describe that to others. If you know that for n equal to 6, there are, what, 6 factorial, that's 720 permutations. If somebody tells you that the probability that permutation is good is, say, 1/20, then you can easily say how many permutations are good. 720 divided by 20, so 36. It's okay to, in terms of modulo billion 7, to compute probability that a random permutation is good. Then when you look at some part and you say, oh, this must be the biggest element, then there is some probability for that. If you look at some part and you know there is probability 50% that this will be good. If you look at some other part, there will be probability of 50% that this one will be good. Good means it satisfies the green arrows from the input. And then in total 25% probability that both yellow parts are good, times probability that big is in the biggest element is exactly here is 1 over size of interval. We can handle we can do this with probabilities too, but code is often simpler, but you need to know combinatorics to count anyway, so maybe better practice with those counting methods. No. Last problem, D. But this one was not needed to pass to the next round. We needed to transform one grid to another, and if the problem was a little bit simpler, then maybe it would be like this. You have some tokens on a grid. Let's say initially tokens are here, then later there, and you need to move one set to another. In one operation, you can move a token by one unit in one of 4 directions. So you can move a token to an adjacent cell with some cost. What's the minimum cost to get one grid from the other? This would be a simpler version of a problem, because actually we also are able to destroy a token and create a new token. But for now, let's say it's this. How do we solve it? This is like matching, where a little bit like matching, where we need to pair up the tokens optimally. If you number the tokens, like 1, 2, 3, and here 1, 2, 3, we need to say which one goes where. If I tell you that this token number 1 goes, let's say, here, maybe instead of numbers I will say pairs. There is pair A, there is pair B, this is B, and the last one is C. Maybe different color for clarity. This is C, this is C. You need to pair them up optimally. If you choose some pair, you will have a cost of moving one to another according to, well, their distance. And there is an algorithm for this. What we are dealing with is matching. So we need to pair up elements of 2 groups with min or max cost. That doesn't matter too much. Or max cost. You can multiply all the costs by -1 and then you have minimum. And a solution for that is called Hungarian algorithm. This is theoretically perfect matching, because we need to pair up all the elements. It works in all of number of tokens cubic. If you don't know something like this, then I would say then you lack some knowledge and you need to read more about matchings and flows. The higher level of matching is flow. And I don't know if they are needed. I use them, but I think flows are needed because we can also destroy tokens and we can create them. Even the number of tokens doesn't need to be the same in the left and right drawing. Maybe there is also a token here and there, also a token here. So we need to transform 4 into 5, and there is cost of destroying and creating a token, and there is a cost of moving a token by 1. Okay, what do we do with that? We can create a graph. There are 4 tokens on the left, and there are 4 tokens on the left and 5 on the right. Just like with matching, let's make a drawing. Let's call it L1, so token in the left or in the first drawing. They are numbered, and they are tokens on the right. Obviously, there are edges between them with some costs. Cost according to the distance between them. Like maybe there is distance 3, and moving by 1 to adjacent cell costs 10 units, 10 coins, and then you get some cost. Maybe here cost is 0 because they are on the same cell. And so on. There is an edge for every pair, because you can move from one cell to another via some path. A lot of edges. What else can we do? We can destroy a token for free, and with this we can, for example, create a new vertex, fake vertex, let's call it F, like fake, and we can say that L4 goes to some fake location with cost equal to the flip cost, FLIP, flip. The flip cost was given in the input. From every left token there is this edge of cost flip, and similarly from some fake vertex on the left there is an edge of cost flip to every vertex on the right. Actually, they could give us 2 different costs for creating a token and destroying it. In terms of words from the statement, it's changing M to G or G to M. And hopefully we can run flow on something like that. We need to also say that we want to do all the tokens, handle them in some way. And for that we create a source and sink. We create those edges all of capacity 1. This is flow terminology. If you don't know flows, you will not understand the solution. Here I think capacity is infinity. Cap is infinity to the fake vertex. From fake to sink also cap is infinity. Everything else in the drawing had the capacity of 1. And now the flow from source to sink, it will go through stuff. We want it to be max flow, and it will minimize cost for free. Not quite there. We are not quite there. Right now, if we do this, because we try to do max flow, the answer, I think, will always be just the number of tokens in total, or the flow size. In this case, it will be 9. The number of tokens in total will be size of the flow, because we are allowed in particular to destroy all the tokens that we start with, create all those tokens, and this will correspond to 9 paths. So it will be like go to L1, go to F, go to the sink. Second path, go to L2, go to F, go to sink. L3, F, sink, and so on. And also from source go to F, R2, sink. There will be 9 separate paths, so capacities are not exceeded. We don't want this to happen. So instead what did I do? I think I destroyed some edges. Destroyed edges, allowing us to flip R's, I think. Let's see. I think those should be destroyed. But I can look up my drawing from the contest. Oh, no, I did something else. I think I destroyed this guy. So I didn't allow flip R's. So I didn't allow creating a new token. So what then happened? Still there are some paths, and with every token given to us, we either choose to flip it, so we destroy it, or we choose to go through some R. And let's say that we choose some paths. There is a flow like this, with 2 paths that go through R's, so 2 tokens in the final target grid are created, but the remaining are not, because what we choose are paths that destroy the tokens, like this. But let's say there are 2 paths like this, and 2 that go and they flip, destroy the tokens. Then there are 3 R's left. I will write this down. If we use paths through some X number of R tokens, we need extra cost of 5 minus X times the cost to flip, where 5 is the number of tokens in the final grid. If you start with 4 tokens, you need to end up with 5, but you started with 4 and you just created 2 tokens on proper positions, and the left you destroyed. You need to now create 3. This is the formula. So for every thing that you didn't use among R's, you pay a cost. Or in other words, we can say that for actually using some kind of R, we get a reward. And I'm not sure how I resolve that at the end, but what I would do now is, now every edge here from R to sink, I put a cost of minus flip, to say flip is the reward for actually using now this R, because thanks to that I will not need to create it later. Oh, I hit the chat, I didn't know that. So this is the reward. It's like saying that, okay, the cost is actually 5 times flip minus x times flip. And now this is part of the, if x times I use an edge among those, it yields the cost of minus x times flip. And the final answer is mean cost of flow minus 5 times flip. This is what you need to print. Where 5 is the number of tokens of type R, so the number of tokens in the second grid. Done. Please guys, don't spam in the chat. And done. But again, if you didn't understand that, likely it means you don't know flows and you need to learn flows. And now we are done, and I think time to finish the stream. Favorite data structure? I don't know. Segment tree is useful. But set is very convenient and powerful. Again, congratulations to everybody who advanced to the next round. Round 3 will, I guess, happen in a few weeks. Because of that, I will make a few streams where I solve hard problems from AtCoder or past editions of Google Code Jam, but mainly it will be AtCoder Grand Contest. So follow on Twitch. I think every Tuesday, on Tuesday evenings, I think I will try to do AtCoders. BBST combines the best of both worlds. Yes, but it's very, I know, artificial. It's hard to understand for a 5-year-old, but a set, how to use a set is very easy. And even I would argue how to use a segment tree and how to implement a segment tree is not 5-year-old kind of easy, but still not the hardest. Join the Discord server and see you around. When will your paid classes video be uploaded? I mean, when it's created, I guess. There doesn't exist any paid classes video yet. I didn't start the paid classes that I was supposed to start in May. Alright, thanks for watching.